Okay, so there were two statements. The first statement was that if my eigenstate of the Hamiltonian is this n ket, Hn equal to n, satisfying this, use some other color, satisfying this, then the eigenkate of the parity operator can be constructed as, so let me call it pi plus minus 1 plus minus pi by 2. Okay, so the eigenstate of the parity operator can be constructed as this pi plus minus n if the n is the eigenstate of the Hamiltonian. So this was the statement, and the proof is very simple, that we just have to use the fact that pi square is identity, because it's the physical requirement that if you do reflect with respect to origin twice, it should come back. So then I use that, and actually I use that to show that the pi itself, the pi eigenvalue, this eigenvalue can be only plus and minus 1. That I did by applying this twice, and this gives me this pi square, and it is identity, so therefore pi is plus or minus 1. So now the proof is very simple, where you have to apply the pi operator on this pi plus minus, which is 1 plus minus pi by 2. And when you do that, the first one just gives you pi operator, second one gives you pi square. Pi square is identity, so this basically is pi n plus minus n, where you plus minus n you take out and you get back this. So this is the proof that this is an eigen state of this operator. Okay. So now comes the theorem. The theorem tells you if h pi commutes and n is non-degenerate. This is a known theorem, but we are just proving it for parity. If h pi commutes and n is non-degenerate, then n is a joint eigenstate of pi and h operator, and they will have eigenvalue plus minus pi for pi operator and en for the h operator. This is also, you know, as a theorem, that if two matrices commute, then without any degeneracy, if there is a degeneracy, then also it is true, but then you have to do something more to prove it, and we'll see that immediately in an example. And we have done plenty of such examples in quantum mechanics 1, that the statement is if two non-degenerate matrices commute, then they must have exactly same eigenvectors, but their eigenvalues need not be the same. Okay? So this is what we know. And then this, notice that this is defined from similarity transformation. If you do a similarity transformation, which means two matrices are connected by similarity transformation, then their eigenvalues are same or eigenvectors are not same. Okay? So need not be same, not can be also if they are trivial. So anyway, so this statement we wanted to prove that if they commute, then this n, if this n is eigenkate of h with eigenvalue en, then this n is also eigenkate of pi with eigenvalue either plus 1 or minus 1. Okay, so this is the since these are the only two possibilities for that. Yes. Okay, so the proof goes as following. All you have to prove is just take the parity eigenkate and prove that is h eigenkate also. So that's what we did. Oops. So that's what we did. We took the parity eigenkate and plugged in into the h eigenvalue equation. This is the statement, and we know here. So that means h pi and it's n, but we know h pi is commuting, so h pi is equal to pi h. So I flip this here, and then h acting on n will give me en, and this is also giving me en. I take out the en, I get back this. Okay, so this was the proof. So now it tells me if 1 plus minus pi n is also an eigenkate of n h with eigenvalue n, then since n is a non-degenerate eigenstate of h, then this object is exactly same as n, or at most it is e to the power I alpha n. Okay, these are the only two possibilities because I started with non-degenerate, and that constitutes the proof that pi and h has a joint eigenkate n of eigenvalue plus minus 1 and en respectively. Okay, and now we did two examples. One was the example where this was not so obvious to construct because it has a it is not an eigenkate on operator, and the common eigenvalue, the common eigenstate you write is not a joint eigenstate, so you have to construct that eigenstate. And if there is a degeneracy, there is a freedom of doing that, because if a matrix has two degenerate solution, then their linear combination is also a solution. That is what we know already. So we want to find that suitable linear combination which is a joint eigenkate of h and pi. Okay? And it can never be a joint eigenkate of h, pi and p because p doesn't commute with pi. Okay, so that is what we did. So we took this Hamiltonian, and its eigengates are this plus minus p, which gives you eigenvalue p square by 2m, and it is not a joint eigengate of this p plus minus p is joint, not a joint eigengate of pi, because obviously because this p is also a momentum eigengate, and momentum and pi doesn't commute. So we cannot use an eigengate which is a joint eigengate of momentum and Hamiltonian to represent the pi if I want it to be pi eigengate also. So I have to construct that eigengate which is joint eigengate of h and pi. So how do we do that? We have to do that by, again, we know the prescription. The prescription is to apply this operator on the p, and this gives me this p plus minus minus p by 2. And when I apply pi on this, I see this is the eigenvalue equation. So that is how we construct that. And simply we can write it more explicitly, that what is exactly the functional form of a plane wave. We have learned earlier also that we can write it also e to the power ixp or cos ixp or cos xp by h bar or sin xp by h bar. So these are the parity eigengate. So here I show it. This is my eigenvalue equation for momentum, and this is my eigenvalue equation of momentum, and here it is the matrix form. I expand it in the x basis. So this is my matrix operator, Hamiltonian operator, acting on this acting on this plane wave solution. We know this is the plane wave solution, of course, and this is I am writing it now in the form that this line. I writing this line in the form that I want this to be not just p but p plus minus minus p, which is the parity eigengate. So if I rewrite it in this way, then I can just expand each of this term. It becomes this, and this is nothing but plus is cosine, minus is sine with a I, and I can put in both sides, then it will satisfy this equation. So now note that the cos will satisfy the plus eigenvalue equation, and minus will satisfy the minus eigenvalue equation. So now I do that just to double check that these cos and sine, they are eigengate. So here I show they are eigengate of the pi operator, and they are also eigengate of the Hamiltonian operator. But this e to the power ipx was not the simultaneous eigengate. And of course, it is not a momentum eigengate, because if I apply momentum operator on cos, I get sine, and sine get cos. So this is not a eigengate of momentum operator, right? So everybody is clear up to this example?
Yes, sir.
Okay. Is Vashna here? Are you following? Okay, probably she's not here. Anyways, so now we will do that for particle in a box. So particle in a box, we got confused because we used a wrong notion of parity. Okay, so if I use this, which is the way we did it earlier, most of the time, most of the textbook write it, which is the particle in a box is from 0 to L. Okay. Now notice this problem is not symmetric with respect to 0. So that is not how you should define parity, because if you reflect with respect to 0, then there is infinite. It is all infinity here, right? So this problem, if you want to apply parity if you want to apply parity symmetry, you have to do it with respect to L by 2. Not the, you have to shift the origin to L by 2. Okay. If you do it carefully, then there is no problem. But I will show you it for this one, because here it is already written in a way the way we are used to handling parity. Okay. So now let's do this case. So we know that in this case the eigenstates are this n square I square h cut square by twice m square, and psi n is this. But in this case it is slightly different, just a matter of representation. The odd eigengates are represented by cosine and evens are represented by sine. Okay, this is the form. So now there is no degeneracy in this problem. So that means what is the theorem tells? The theorem tells if there is no degeneracy, then automatically the parity eigengates are also eigengates of the Hamiltonian. Okay, that was not the case of free particle. That's why we had to take a linear combination that is joint eigengate. Okay, so let's demonstrate that, and that's where we got confused. So since there is no degeneracy, this is what we proved. This is exactly same as this. So let's try that. So pi acting on this operator. So we want to first start with the parity eigenvalue equation. So now I put the x. I basically do this here. okay, and summing over x prime. So if I do that, this is what I get, this line, and then I split these two terms. Now this pi, I know definitely how it acts on x. It makes it x and minus x. Here also it makes x and minus x. Now if n is 1, 3, 5, which means odd eigenvalue, then this xn is cos, then minus xn is cos minus x. Okay, so this is what I write in both sides. For minus, they will cancel each. They will add. Sorry, they will cancel each other, and for plus, they will add. So the minus is a trivial statement. It is not even because it's of course always true. If you add pi on zero null vector, you will get zero. Okay, notice that this is not a null vector, by the way. A null vector is if I have an operator acting on a non-trivial vector or acting on some non-trivial vector and giving me zero, that is actually null vector. That is what we call null vector. But here it is actual zero, which means it is 0, 0, 0, 0, 0. And it is trivially null vector. That is, of course, always give you zero. Okay? Because when I cancel it, it's only zero. So that has no meaning, this statement. So the only possibility is this acting on cos will give me cos with a plus in front. So this is a parity eigenket. So the odd eigenvalues are automatically a parity eigenket with plus parity. Okay. Now for even, I do the same. I play the same game. In this case, since this minus sign comes out, then only minus will survive. The plus will give me the trivial zero. So this will give me the minus. So automatically the energy eigenkets are also parity eigenkets. Okay, that was the theorem. Okay, everybody clear about all this? Comments? Am I connected? Confused? Too sleepy to understand what's happening?
It's
So the
fine.
null vector thing.
Yeah, sorry, you are saying
So
something?
yes, the null vector thing. Could you repeat that particular thing?
Yeah. So see, this is a simple algebra. This is a simple algebraic statement. Okay. We know what is a null vector. Null vector means if I act a operator on some vector, okay, on some vector, and that gives me zero. So I call this V as null vector, right? This is what you learned probably in mathematical physics, that there is a rank nullity theorem that tells you rank plus number of null vector and rank of a matrix should sum to zero. But this vector so let's you can try it with write some matrix. Okay, find the null vector and you will find that this null vector could be something non-trivial. So null vector means something that satisfies this zero eigenvalue. Okay? This means zero times that vector, right? So now let's say I have some matrix A, B, C, D, E, F. So let me make it Hermitian. C, F, E, C, F, G. Okay, and it's not its vector is M, N, R. Okay, M, N, R. So then if M, N, and R, M, N, and R, all of them, if all of them are non-zero, then it's a non-trivial non-vector, null vector, right? But if M equal to N equal to R, all of them are zero, then it is obviously every matrix have that null vector, right? All the matrices in the universe have, if you multiply them on a vector that is 0, 0, 0, they will give you zero. So that is why this is a trivial statement. There is nothing fun, substantial into it, right? When I write this, when this vanishes and you act pi on that, pi acting on zero will give you zero, zero vector. Right? Cos this function is a vector, you know that it's an infinite dimensional vector. So that's why it's a trivial statement. There is nothing profound in it. That's why I can discard that statement. It's not that I'm throwing away a solution that has a physical meaning. Okay, makes sense?
Yes, sir. Thank
Yeah.
you, sir.
Now these null vectors, by the way, now that you came to that point, there is a very profound problem with this null vector. So there is some partial progress we made with Prarthana in a previous semester to understand this. If some of you are interested, can study that problem also. So the problem is following: if I have a Schrodinger equation on a lattice, which means let's say the kind of problem you study in solid state physics. If I have Schrodinger equation on a lattice, and I want to ask what solution gives me zero eigenvalue, which is equivalent to finding this null vector. What non-trivial solution give me zero eigenvalue? Okay? So it turns out what in such system we looked at a particular class of system. It turns out that there are some zero eigenvalue, and this is something actually we found in a different research problem that we published earlier. You can also look it up into that. There, and they are also these matrices on lattice become something called adjacency matrix on a graph. So the question becomes, what are the null vectors of the adjacency matrices? They are called graph zeros. So if some of you are familiar with some non-trivial math, you will know that these kind of things are called graph zeros, and these things, these kind of problems where one analyzes these, they are called matching problem. And I will tell you at some point of time later why they are called matching problem. But the problem was that finding null vectors finding null vectors of a adjacency matrix with weighted adjacency. So that weight could be a phase factor also on a graph. So this is the problem of finding zero modes. Zero modes or zero eigenvalue solution, and they are also very important in various other classical problems also, not just quantum problem. So there are these networks. These network zero modes are very interesting because these modes tell you how many ways you can. So I will just a moment, I'll tell you zero modes of Schrodinger equation on a lattice. And they are also similar to mass certain problem. For example, you can say I make a network of mass and spring. Okay, network of, this is again something you will learn in solid state physics, this kind of picture, because you can think a solid is basically a vibrating atom, right? So now I can ask this mass spring. So you can try this. So if I write a coupled equation, so the mass spring will follow some coupled differential equation, right? You have done this problem, definitely you have done this one, a pair of mass. This is also an experiment in your lab, by the way. Oh yeah, very good, this is an experiment in your lab, so I'll tell you that. So zero modes of Schrodinger equation on a lattice, and they are equivalent to non-deformed solution of mass spring network. So this means this when you write down this coupled differential equation and linearize it, write it in a matrix form. So you can show that these zero modes are basically those solution that doesn't deform the lattice, that which means all the springs are either stretched or squeezed at the same time. So now I have seen this setup in your lab. I don't know if you remember that. So there is a pair of pendulum coupled by a spring, right? You know this setup, right? Do you remember this setup? What?
Yes, sir.
Nobody have ever entered in the lab?
Yes, sir, we have seen.
So you remember there is a motion where these two move like this, move together in phase. So such that the spring is not stretched. Okay, the spring is exactly at the same size, or it can move like this, two ways. Then the spring is stretched and squeezed. So these solutions where the spring is not stretched, they are like this solution whose eigenvalue is zero if you write the coupled differential equation in a matrix form. So they are of profound importance in Schrodinger equation and lattice. These zero modes are zero energy solutions, this non-trivial null vector. So it's very interesting to know what is the wave function of that. So if I write the lattice, so let's say it's some lattice Schrodinger equation. So H psi equal to 0 psi. So I want to know, if I write the H matrix for this, what psi gives you the 0 psi? What's non-trivial psi, not the 0, 0, 0, 0 psi. Okay. So those wave functions, they are often really related to something called Majorana mode, Majorana zero mode. So I am very recently I reviewed a paper which tried to detect this Majorana mode in a STM experiment in some scanning tunneling microscopy, and they gives like certain if you connect it to in a particular circuit, they gives a voltage. At zero voltage you will get a current, and that is very interesting, and there are many controversies regarding that. There were two papers written earlier, they were later challenged, saying no, you have what you have seen is not a Majorana zero mode, it's something else and all that. It's a very deep subject. So this is something you can think of. So non-trivial zero modes, non-trivial null vectors in lattice Schrodinger equation. So this could be an interesting term. Okay. Okay. So now let's come back. Let's come back to the point which we were doing last time. So, okay. So this is just to clear the issues from last time. So now let's talk about something different. So last time we ended with this example that let's say I have a symmetric double well. Okay, symmetric double well means I have a potential barrier in the middle. It's a particle in a box, but I put up a potential barrier at the middle. Okay, so x equal to 0. And we argued that there are two solutions, two lowest energy solutions are these. One is this. Okay, and the other is this. Okay, this region, this is exponential, and this region, this is oscillatory. This is the symmetric solution, this is the anti-symmetric solution. And we also said that H is this is parity symmetric because the Hamiltonian itself has a parity symmetry. So I can write it for H pi equal to 0. Also, we argued that ES must be less than EA because EA has a node. Okay. So now I said, let's say I want to study the dynamics of this problem. And I want to take also to note that these S and A are also eigenvalues. Of course, it has to be. That's the theorem says if there is no degeneracy. So this is the simple case where S and A are also eigenvalues of the eigenkets of the pi and H operator. Okay. Now I want to ask the question: what if I start the particle on the left side, entirely on the left side, and I want to study the dynamics? Of course, I have to do something like that. I have to start with a state that is not an eigenstate of the Hamiltonian. If I start with a state that is eigenstate of the Hamiltonian, then the dynamics will be trivial. Okay. So let's try to do that. And so let's start with a state which is on the left side. Or on the right side. Okay. So one case is basically, this case is, I'm adding these two. So the L is basically this is asymptotically go because this is not infinite, and right is basically okay. Now I want to ask, if I start with this, what will be the dynamics of the system? And it is very simple. You already know that what to do. So I want to ask what is L at t0 equal to 0. If I start with L at t0 equal to 0, what is that at time t? Okay. We know that we have to apply e to the power minus iht on L, and this gives me 1 by root 2 e to the power minus iest is plus e to the power minus eat a. Okay. Now I can polish this equation a bit by writing so now notice what is happening here, that this means that this solution will oscillate between S and A. Okay, not S and A, between left and right. Why? Because there will be a time when t is equal to t by 2, which is 2 pi h bar by 2 ea minus es. So this is the time when this becomes minus with e to the power I pi basically. Okay, so I write at what point this will become e to the power I pi, and that time this thing is basically S minus A, right? Which is R. So this is the kind of two-level system we have studied before. So L and R, it goes in T by 2 period, it goes to R, and then it comes back at T period to L. Okay. So this will be an oscillatory solution, and the oscillation frequency will be EA minus ES by H bar. Okay. Everybody got this point? Comments?
So can you repeat the last one?
Okay. Did you do the two-level system problems in quantum mechanics 1? Yeah, yes, no, didn't do, forgot. There has to be an answer, right? Yeah, can you comment something about that, the two-level
Yes,
system?
sir. Yes, sir.
Yeah, so do you see, do you see how it is exactly the same?
Yes, sir.
Yeah, so the problem is only that. So yeah, so if you are looking for something else, then it will become unnecessarily complicated. It's just a two-level system problem where I apply IHT on S and A, it becomes S and A, and the solution, if I take it common, this becomes S plus this. Okay. Now there will be a point of time when EA minus ES T by H bar is equal to pi. Okay. When that happens, so this is or minus I pi, whatever. So if e to the power minus I pi is what? Minus 1, right? So when it becomes minus 1, then this solution is basically 1 by root 2 e to the power minus I S T S minus A. So I started at time t equal to 0 with S plus A, which is L. Okay. And after a time, after a certain time, I reach to this state, right? Which means I start with L, and after a period of T, I define that as T by 2, because there will be also a period when it comes back to S. It's a periodic motion, oscillated. So that I call it T, and this I call it T by 2. And this time or this frequency at which it happens, that basically tells you the solution will be nothing but this. It will go between something like this. So this is your L, this is R, and this is L. Right? With time, this is the wave function, let's say. So this is what it will do with time, right? Everybody follows that?
Yes, sir.
Okay. So now this is the solution. Now what is interesting about it? Why am I doing it this context? So now notice this frequency, the time it takes to go from one of that to other is a function of EA and ES. Okay. So now if it happens that if there is a scenario that does the following. So let's say I have this potential barrier and I increase this. So if I keep increasing thing, what will happen? If I take it to infinity, what will change about the problem? This is also a problem we did extensively in quantum mechanics 1. Nobody knows? If my solution here
Sir, can you repeat the question once?
yeah, this is my if this is my solution, right, for a v finite. If I take the v to infinity, if I take this v to infinity, then how this solution will change?
Sir, it will get divided into two symmetric parts, like
Yeah,
left and
so
right.
this will be divided into two symmetric wells, right? Because these have gone to infinity. So the solution will be this, right? It is basically splitting into two problems. So that means the difference. So now this is my symmetric solution, and what will happen to this solution? This will go to this, right? Everybody got that?
Yes, sir.
Okay, now is there a difference between this and this, these two systems, the symmetric and asymmetric, in this limit?
Sir, asymmetric system, the second one is not possible, right?
Why?
Sir, like if it's ground state below the, how can it be like below zero in that case?
What are you talking about? What is this you think? What is it you think? This subject? Why it cannot be below zero? What cannot be, Arjit? Can you tell me what cannot be below
Nothing,
zero?
sir, nothing, sir. I actually got confused with like ground state. Actually, it's asymmetric one. Sorry, sir.
So, okay, so can you clarify what is the correct statement? You said you got confused now. So now what is the statement? What is the correct statement? Nobody knows about this anywhere. Somebody else? How about Biroja? Can you tell me? Can you tell me this? Let me ask something even simpler. Particle in a box, right? What is the difference if I write this ground state? What is the difference between these two wave functions? What? I mean, don't tell anybody that I taught you quantum mechanics. This is really embarrassing for me.
Sir,
So we know that yes.
is it like phase difference?
So
Or
what's the difference in what does it mean for that? So this wave function is sine n pi x by L root 2 by L, and this wave function is e to the power I pi root 2 by L sine n pi x by L. There is no difference between them. Both of them are solution because it's an arbitrary phase factor, right? So this solution and this solution are exactly same. So both of them, if this is EAS and this is EA, they are both same. Okay. If that is the case, so that means the omega is going to 0 because omega is EA minus ES by H bar. Okay. And that means the time period for L to go to R goes to infinity because this goes to 0. Which means if I make my V naught infinity, if the barrier is very high means infinity, then the system starts in L and stays at L, right? It cannot go to R. It can never go to R. Okay. So even though L and R are symmetric solution, this system will break the ground state of this solution will break the symmetry of the Hamiltonian. Okay. So you will find that the system will be always in a state L or R. L or R are not H pi eigenkette, and they will break symmetry of H. Okay. So this phenomena is called spontaneous symmetry breaking. Okay. And there are many examples of that. If you take advanced courses, you will learn this in StatMech and everywhere, and not just StatMech, particle physics also. The one simple example of this is Ising model. So let's say I have a model, is it, okay, which means this model implies if these two spins are in same direction, then it will have a lower energy compared to if they are in opposite direction. Okay. So actually you need this J needs to be negative for that. So this is what you know. This is ferromagnet. This is a model of ferromagnet. So Ising's system means all spins pointing in one direction. Okay. Now I can also point all the spins in this direction. That will be exactly the same energy. But there is an infinite energy barrier between these two. Because if I want to flip all the spin in the opposite direction, then the energy cost I have to pay is infinite, right? Because if I flip them one by one, each of them will cost a huge amount of energy. But after I flip, they are exactly the same energy as before. Okay. So this thing, although these two configurations are symmetry, if you find your system in this configuration, you will never find it in the other configuration. Okay, this thing is called spontaneous symmetry breaking. And then there are more interesting examples of that. For example, think of a ferromagnet. A ferromagnet means all the spins are pointing in same direction. So this is Ising. Ising means they can be either up or down, nothing else. But let's say if I do this SISJ, which means Heisenberg, okay, you will learn that in stat mech or condensed matter. So here all the spins are pointing in one direction is your ground state, it's ferromagnet. But they can also point in this direction. This is a dot product, which means I can rotate it in any arbitrary angle. They can be in this direction also, right? They can be in this direction also. So there are infinitely many configurations which are related to each other, but they cost infinite energy to go from one to another. So these things are drawn by a Mexican hat potential. So that means each configurations are on this line. You can continuously reach from, in order to reach from one to another, you have to give a infinite potential penalty. Okay. So if you find a system in one of these configuration, it cannot go to the other configuration. Okay. So this is the statement of continuous symmetry breaking. There is another example of that which we discussed in previous semester in the context of ammonia. So for ammonia, we have seen that ammonia has this tetrahedral structure. Okay. Ammonia, no, this structure. Ammonia has this tetrahedral structure, and this structure, which is down pointing triangle, down pointing tetrahedra. So there is a huge energy gap between these two. Okay. So it turns out this time period is of the order of 10 to the power 6 years for ammonia. And if you want to see one to another, okay, one getting spontaneously converted into other because of the Hamiltonian dynamics, then you have to wait that much time. Okay. But you can activate it by pumping it some energy, which is the source, which is called measure. MA is here because this energy is in the microwave region. It was discovered before laser. Laser is for light, measure is for microwave. And if you remember, I gave you this comment that who was this guy? Clauser was failing in course in Columbia. His senior Towns was also failing in the same course in quantum mechanics. He invented this measure and got Nobel Prize for that. Okay? To find how to drive this transition by using a optical disturbance, which is this measure. Now there is one more interesting point about that. This is discussed very briefly in Sakurai. So it turns out there are these sugar molecules, that we all have biological systems. So there are a left type sucrose and right type sucrose molecule. Okay. So if you prepare them in laboratory, which means, so what does it say? It says that if under spontaneous dynamics, this can go one to another, and if you produce them but if there is a huge energy cost, which means of the order of like this kind of time, then if you produce in L, you will never go in R. Okay? But it turns out if you look at nature, then you will find all the molecules, almost 99.99% molecules are of R type, not of L type. Okay, one of the two types, which is very hard to explain, because why did it happen if I produce it in a statistical ensemble? And in fact, if you try to produce these sugar molecules in lab, they are produced in equal amount. But then what process of nature did it like that is a interesting problem. Okay. And this can be actually, one can make it more and more complex. For example, if you see why all of our heart is on the left side, not on the right side. So it is kind of, so if I think a human body as a quantum state, and if I start with the ensemble where it is in the left side, then by quantum dynamics it can never go to right side. Okay? But then one should ask that if I produce a random ensemble of such systems, then there will be equal number of left and equal number of right. But that doesn't happen. Almost all of them are left. One or two are probably right. This is an anomaly, abnormality. Okay. So this kind of why nature picks one of the two, left or right, it's not, there is no answer to that. Okay. But if they do, then they are stuck with that choice, because the time it takes to go to the other by quantum dynamics is effectively infinity. So this is basically the statement about this kind. This is a very simple problem, but these problems are understanding this related to some of the profound mysteries of nature and also some interesting technology, which we will discuss. Come back again discussing that when we'll do the time-dependent quantum mechanics. Okay, now I'll end this chapter with one thing, which is selection rule. So selection rule is something you have learned extensively probably in chemistry and in spectroscopy, atomic spectroscopy. Selection rule basically tells
Sir?
you, yes,
Sir, can here symmetry breaking you said, right?
yes,
In that since one form can't be transferred to another form,
yes.
I mean that is the symmetry breaking, or
That is the meaning of, no, that means that even if these two forms are equal, okay, these two forms are equivalent, these L and R, in this case, for example, L and R are equivalent. If you start with one, which is a symmetry broken, you cannot go to the other one. So if your system's initial state is a symmetry broken state, it will remain in that symmetry broken state. Okay, that is the meaning of symmetry breaking. That is the meaning of. So you will find the system in a state which is not an eigenstate of the Hamiltonian and a symmetry broken state. Okay, that is the meaning of that.
Sir,
Yes.
initially both the number of both the states should be equivalent. So anyways, let's say some of the states are in like left configuration, some are in the right configuration. So still the number would be equal, right? Like the probability for both of them.
Which case are you
So
talking about? Double
like
well?
this case only, you said, like from one state, like from one configuration to another, we cannot go
Yes.
because of this reason. But
Yes.
initially, the probability of both the states are same. So number of
No,
uh,
if you prepare a ensemble of system without any selection, then there will be probability half, that half of the system in the ensemble are left, half of them are in right. Yes.
okay, so like generally in case of tetrahedral structures, like in like
Yes.
any molecule,
Yes.
we yeah. So in that case, we see that both of them, like it flips, like both of them are correct. But why is it like in this case only we are seeing that it cannot flip that way?
No, no, no. What do you mean by it flips? See,
Like
the
I see,
point
like
is, if you
is it
start with this, if you start with this structure, then the other structure is costly, right? And when does this direction matter? So again, you must have forgotten this ammonia problem. This direction matter only if there is a reference field. So let's say you have a magnetic field. What is pointing up and what is pointing down? That to tell that you need a field, right?
yes, sir, yes,
So that field when you have that field, then it is a huge amount of energy cost to flip this thing. Okay,
yes, sir.
some kind of field. Okay,
Okay, sir. Okay.
yeah. Okay, you need some direction. Okay,
so
now yes,
so is it like anything antiparticle particle also the number
yeah.
related to this,
This
sir?
same question is there for antiparticle particle also, and that's a separate discussion which I'll not have now. Maybe in the relativistic quantum mechanics section, because this is not like a double well. Antiparticle and particle are not like double well. They are not two solutions of this kind of symmetry. So antiparticle particle has a very different structure, but that question is also there. Why there are all particles and not antiparticles? Yeah, but it's not this. This is not in this framework. That is not a case of spontaneous symmetry. Or maybe one have to think carefully. But this is not like this symmetric double well. Antiparticle and particle, the concept of antiparticle and particle are needed for a different reason. Okay.
Okay.
Okay. So this is more about, if I have these symmetric solutions, then how can I why a natural system will be generally found in a spontaneously symmetry broken state, which means it will be found in a state, most likely if you do an experiment, you will find a system in a state that is not a eigenstate of Hamiltonian or the parity, because parity or something equivalent of that, because it once it starts in such a state, it can never go to the other. Okay. Okay. And this is also the minimum energy configuration for magnets and all that. So there are many profound ideas related to that, like Goldstone theorem and all, which you will learn eventually if you take those courses. Okay, so this is your selection rule point. So selection rule is what? Selection rule tells you if there is a transition, that transition can or cannot happen under certain scenario. So that is what is the meaning of selection. So let's say I apply this parity transformation and O plus goes to O plus, and this is parity even, and if it is parity odd, so it is just like that x, right? Pi x pi is x minus x, and pi is L, right? This is just like that, but I'm saying it for a generic operator. So let's say the operator that doesn't flip, that is minus O minus. Okay, that the flip, the one which doesn't flip is O plus, the one which changes sign is O minus. Okay. So now let's say I take two states K and L which are of opposite parity, which means they are parity eigenstates but with opposite eigenvalue. If one is plus 1, the other is minus 1. That means pi k is plus minus k and pi L is minus plus L. Okay. Now if this happens, then K O plus L is K pi O plus pi L. Okay. Now this and this will give me opposite. So minus K O plus L is 0. Why? Because this object is equal to minus of itself. So the only way it can happen if it is 0. So now I can think another statement. Let's say I take another state which is M and N, which are of same parity. So if they are of same parity, then I'll see now this is minus. So this is again minus M pi O minus pi L. Sorry, pi O minus L. So that is equal to 0. So what does it mean? So this means, so matrix element of an even operator is 0. Between states of opposite parity. So this is what we learned from this statement. And this statement says the opposite. That is, odd operator is 0 between states of same parity. So this basically tells you, this gives you a selection rule. It tells you, you cannot go from this state to this state under the action of parity. Okay. So that means these two states. So why these matrix operators are important? Because this tells you, if I start with a state K, how I can go to L, okay, by action of this operator, right? So it says under the action of this parity operator, you cannot go to that state. So that shows certain transitions are impossible. So this constructs a set of selection rules, and this particular rule was is called, this particular rule that I written down here, it's called Laporte's rule, which is somebody who discovered it without knowing about parity from experimental observation and all that. Okay, by doing some what will I say, phenomenology. So selection rules are very important, and now you can see a direct a use of parity or this kind of operator. The use is following: if this kind of symmetries exist, then certain transitions can never happen. Okay? Now you can see a more direct consequence of if why do I care about these symmetries? Because it clearly makes you certain things forbidden. So these are actually ways people look at these experiments also. If they see some transitions are forbidden, then they guess that system has some symmetry. Okay? Something is going to 0, right? Totally 0. So then they guess that system has some symmetry. and that symmetry, then one can try to construct what kind of symmetry is causing that. So this is generally one of the very useful thing about symmetry, is that it makes things to zero, certain things to zero, and if something goes to zero, they are noticeable. They are noticeable, and then you can construct backwards for a theory for that. Okay, so this is the idea. So this is the whole idea of parity, and everything I wanted to tell you about parity. The next topic I'll do is time reversal, and today I think I will not start that, but you revise these aspects of time reversal in these three contexts. So let me just initiate the topic as you learned in classical mechanics. Okay? All classical revision of time reversal. So we learned in Newton's law. So TR, Newton's law, they are time reversal invariant. Fundamentally, not with friction. All holonomic Newton's law. And why I'm not including friction? Because friction has microscopic origin. If you consider the microscopic origin, then it is also time reversal symmetry. So mx double dot is minus grad v, which means if xt is a solution, then x minus t is also a solution of the same equation. Okay, this is the simple statement that Newton's law is time reversal symmetry. But we know ED is not time reversal symmetry. Okay. Why? Because we know if a object, so time reversal means motion reversal. If an object is moving in this way, a charged object, it will produce a magnetic field like this. But if I flip the motion, which means make it this, then the magnetic field will be this way. So that's the simplest demonstration that how electrodynamics is not time reversal symmetry. So what's the consequence of that? The consequence of that to the Maxwell's law is following. So this is my Maxwell's law. In CGS unit. And Lorentz law. So we will see that this law is intact. This law is not, because it will pick up a, no, this law is also intact because it will pick up a minus sign here, and minus, current is also opposite, right? And okay, no, I think the statement is not correct. So ED, and if you want to keep ED time reversal symmetric, then you have to be careful. You have to do the following things. You have to take into account. So of course the laws of motion has to be. So sorry, this is the wrong statement. So the laws of motion have to be, the relation between objects have to be time reversal symmetric, but quantities need not be. Okay. So all the ingredients of Newton's law had no problem, but ED has this problem because under time reversal symmetry, E goes to E, B goes to minus B, rho remains intact, J goes to minus J, and velocity goes to minus B, right? So then if you do all these transformations in this set, you will see this equation is protected. This is also protected because this will give minus, minus, and minus. This is also protected because this is minus, this is also minus. This is also protected, this is also protected, and this is also protected. Okay. So ED is time reversal symmetric, but the quantities has to change accordingly. Okay. Now let's say I want the same for quantum mechanics. And we demand and we ask that what should I do here to keep it time reversal symmetric, because I clearly see that x minus t is not a solution. Is not a solution unless you also take I2 minus I. Okay. So in order to, so this is this set of rule for quantum mechanics will be when x t goes to psi x minus t, then I must go to minus I. So you need a complex conjugation somewhere, right? So this is the condition for time reversal symmetric invariance of quantum mechanics, and that is what we will start to build up what is the formalism for that? How should we represent those operators? Now there is one more point I want you to think about, which I mentioned but I didn't explain. I said that this, if I take a state psi and phi, and I do a symmetry transformation u psi and u phi, then I said this must be equal to psi phi mod star. Okay? This thing must be equal to this, not mod star, just star. Okay? Why did I forbid this? Why did I say that? First of all, because what I want is u psi u phi mod square is equal to psi phi mod square. Okay? This is what I wanted, and I said this is the condition, but I didn't discuss, and that's what I want you to think, why it is not like this. Why I am not allowing this but just saying star. Okay? Think about it. Okay, questions? Okay, if none, that's all for today.
Sir,
Yeah.
can you repeat the last question, sir?
Yeah, so do you remember the Wigner statement? I said if u phi is u psi, this must be equal to psi phi inner product star. Why? Because a symmetry transformation is something that keeps the probability intact, which is the observable, okay? Or measurable. So this is the probability, which is the square. So star ka probability and this probability are both same, because when you square them, the star doesn't matter. But it doesn't matter also if I multiply it with an arbitrary phase factor, right? But then why didn't I say that? Why didn't I include that in the discussion? I came to the conclusion that all transformation must be unitary or anti-unitary based on this, that this transformation is equal to star of the inner product, right? Do you understand the question now?
Oh, you are like, why alpha like not?
Why I'm not allowing that?
Okay.
Okay, that's all.